Good morning. It's September 1st, and this is your daily brief in science. Here's everything you need to know. A recent study suggests that clopidogrel may be more effective than aspirin in preventing serious cardiovascular events in patients with coronary artery disease. The research, published in The Lancet and presented at the European Society of Cardiology Congress in Madrid, analyzed data from 7 clinical trials involving nearly 29,000 patients. The findings indicate that patients taking clopidogrel experienced a 14% reduction in the risk of heart attacks, strokes, and death compared to those on aspirin. Importantly, the rates of major bleeding were similar between the two groups, showing no increased bleeding risk with clopidogrel. Clopidogrel is also more affordable, costing less than 4 pence per day, whereas aspirin costs about 2.5 pence per tablet and is widely available as a generic medication. These results challenge the long-standing recommendation of aspirin as the default lifelong treatment for coronary artery disease, which affects over 300 million people globally. Experts, including Professor Brian Williams from the British Heart Foundation, suggest that these findings could influence prescribing practices, potentially favoring clopidogrel for certain patients. However, further research is needed to assess the cost-effectiveness of clopidogrel and to update clinical guidelines accordingly. Given that 2.3 million people in the UK have coronary artery disease and often take aspirin long-term, this new evidence could prompt a shift in standard care. The study's data showed that both medications had similar rates of major bleeding, alleviating safety concerns. Clopidogrel's greater efficacy was consistent across various patient subgroups, including those with poor drug responsiveness and those who had stent procedures. A new global study using satellite imagery over 2 decades reveals that Earth's land ecosystems do not follow a uniform seasonal pattern. Instead, they experience complex, asynchronous growth cycles that challenge the traditional 4-season model. The research highlights regions with Mediterranean and tropical mountainous climates as hotspots of this asynchrony, where neighboring ecosystems have vastly different timings for plant growth and rainfall. These irregular seasonal patterns are linked to Earth's biodiversity hotspots and could influence evolutionary processes like genetic divergence and species formation by impacting reproductive cycles. Advanced analytical methods, including harmonic regression and machine learning, were applied at a 5.5-kilometer resolution, and the findings were validated with ground-based data from Phenocam and FluxNet stations. An interactive Google Earth Engine application now allows the public to visualize these phenological patterns and asynchrony maps, with open-source data and code available for further research. The study also demonstrates practical applications, such as correlating satellite-derived phenology with coffee harvest schedules in Colombia, which could aid in agricultural planning and climate adaptation. Understanding the variations in seasonality is essential for ecological research, climate change assessments, and managing agriculture and conservation efforts. This research lays the groundwork for exploring how seasonal asynchrony influences biodiversity, species evolution, and ecological interactions, with significant implications for conservation and climate resilience. It shows that Earth's phenological cycles are more intricate and less synchronized than previously thought, prompting a need to revise traditional models. Environmental factors like precipitation, temperature variability, topography, and vegetation heterogeneity are primary drivers of local phenological differences, as identified through models such as random forest analysis. Remote sensing patterns are also linked to genetic differences in species like Brazilian anurans and tropical birds, supporting the idea that asynchrony can promote speciation through mechanisms like allochrony. Satellite data can predict real-world flowering times and genetic divergence, exemplified by coffee harvest cycles in Colombia, where local seasonal cycles can be as out of sync as those between hemispheres. In tropical hotspots, the relationship between climate and phenology is weaker, indicating that other factors like biotic interactions and microclimatic heterogeneity also play significant roles. A new breakthrough in cardiac support technology has shown promising results in improving survival for patients with cardiogenic shock related to STEMI. The Impella CP, recognized as the world's smallest heart pump, is the first device proven in a randomized controlled trial to significantly enhance both short-term and long-term survival outcomes. The Danger Shock trial, involving 360 patients across Denmark, Germany, and the UK from 2013 to 2018, demonstrated that patients supported with Impella had a 16.3% absolute reduction in mortality at 10 years. This long-term data also indicates patients gained an average of 600 additional days alive. Cardiogenic shock complicates up to 10% of the approximately 750,000 STEM1 cases annually in the U.S., making this advancement particularly relevant. Impella supports the heart by temporarily taking over its pumping function, allowing the heart to rest and recover. It can potentially reduce the need for heart transplantation or permanent support devices. The trial's results led to the device being recommended at a Class 2A guideline by the American College of Cardiology and American Heart Association. Johnson & Johnson emphasizes its commitment to addressing major health challenges through innovations in cardiovascular solutions and medtech tools. The long-term survival benefits, confirmed by data published in the New England Journal of Medicine, underscore the device's potential to transform treatment for severe heart failure cases. A research team at KAIST, led by Professor Kwang-hyun Cho, has developed a universal algebraic technology that can identify and restore altered gene networks in cells. This breakthrough addresses long-standing computational challenges by enabling rapid searches for gene control targets within large and distorted networks. The technology allows scientists to predict stable cell states and understand how controlling specific genes can revert abnormal cellular responses to normal. It uses mathematical techniques like the semi-tensor product and Taylor approximation to simplify complex calculations of gene interactions. The team modeled gene interactions with Boolean network diagrams and visualized cellular responses through landscape maps. Their method has been tested on various gene networks, including bladder cancer cells and immune cell differentiation pathways, demonstrating its ability to systematically identify core gene control targets. The research was published in Science Advances on August 22, 2025, with contributions from KAIST students and support from the Korean government's research programs. Professor Cho highlighted that this innovation is a key step toward developing the digital cell twin model, which aims to analyze and manipulate gene network phenotypes for applications in medicine and life sciences. Scientists have uncovered microbes trapped beneath the Pacific Ocean floor that have survived for over 100 million years. These microbes were retrieved from sediment layers nearly 5,700 meters deep, living in nutrient-poor and toxic conditions. Laboratory experiments confirmed that some of these ancient microbes can actively grow and multiply, with populations increasing more than 10,000 times in just 68 days. This challenges previous assumptions that life in such environments is limited by age or nutrient availability. Researchers used the drillship JOIDES resolution to extract sediment cores from depths of up to 6,000 meters below the ocean surface, revealing microbial communities that persisted despite extreme conditions. All sediment layers contained detectable oxygen, indicating that oxygen can penetrate deep into the sediments and support oxygen-dependent microbes over millions of years. Microbes were not fossilized, but living organisms capable of division after lying dormant for tens of millions of years. Professor Stephen DeHont explained that these microbes likely remained in place for 100 million years, with their growth limited by scarce energy. The discovery suggests that the deep subsea floor biosphere is more extensive and resilient than previously thought. It raises questions about how these microbes survive with such low energy levels, which are millions of times lower than surface microbes. This research broadens our understanding of life's limits and resilience, even in environments like hydrothermal vents or nutrient-starved sediments. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.